In the first lecture on properties of central force fields, you have discussed actually the two important properties of central force field. The first one was that the angular momentum of the particle moving in a central force field remains constant. And secondly, we have seen that the motion in a central force field always takes place in a plane. We have explained these two properties in the first lecture on this series. Now today we will actually deal with two other important properties of central force field. The first property which we are going to discuss in this lecture is that the areal velocity of a particle moving in a central force field is constant, or mathematically you can say that dA by dt equal to constant. Actually here dA is the area vector described by the particle in a central force field in a time dt. So since in time dt the area vector described by the particle is dA, so in unit time it will be dA by dt. And the area described by the particle in unit time is known as its areal velocity. Okay, so we simply say that the areal velocity of a particle moving in a central force field is always constant. Okay, in fact, in other words, this statement is also stated like this, that the position vector or the radius vector drawn from the center of force O to the particle sweeps out equal areas in equal times. In fact, when we will prove this result, then we will explain this second statement. Okay. Actually, this property is also known as law of areas, or when we will actually discuss the three planetary laws of motion of planets given by Kepler, then you will see that this is nothing. This is simply the Kepler's second law. This property is simply the Kepler's second law. We will see later on. Okay, so this is the third important property. Now the fourth property which we will discuss in this lecture is that the central forces are conservative force fields. Central force is a conservative force. We will discuss it. Now let us start to explain the first property of the central force of this lecture. This is law of areas. As the property says that the areal velocity of the particle moving in a central force remains constant. Now let us see this figure. I have shown a trajectory here. This curve is just a trajectory of the particle moving in a central force field. And consider that this point O is the center of force. That is, this is center of force, you can say. Okay. Now we consider that at any time t, the particle is at this point P. I have mentioned it here. And its position vector is in fact r. Now after a very short interval of time, that is after infinitesimally interval of time, let us say dt, the particle moves to this point q. You can see. Now in general this pq will be actually a curvilinear path, but if you consider that dt is very small, then this point q will be very close to p, and you know, if q and p are very close to one another, then this pq will be almost straight. So pq will be just a straight line, provided that we have assumed that this time interval dt is very small, because the very short length of any curve is straight. Let us see this figure. If you consider that this part of this curve, that is between A and B, then this will be a curved path. But if you consider this very small path between C and D, this will be almost straight. So as I have assumed that dt is very small, so PQ will be almost straight. Okay. So consider a particle. Consider a particle moving in a central force field. Moving in a central force field with center of force at O. O is the center of force. And at t equal to t, the particle is at P, and at t equal to t plus dt, it is at Q. Okay. And I have assumed that this arc PQ subtends an angle d theta here at the center of force. All these things have been shown in the figure. Okay. And if dt is very small, it means this is infinitesimally small, you can say, then PQ will be almost straight. This is almost straight, and OP will be almost equal to OQ. Okay. And both are actually equal to R, say. Okay. And the figure OPQ, see the figure OPQ, this OPQ, this will be just a triangle, but this will happen only when you assume that dt is infinitesimally small, that is the point Q is very close to P, and this PQ is just a straight line. So OPQ is a triangle in this condition. Now in this condition, what will be the area swept out by the radius vector OP in this time interval dt? You can see that the area which this radius vector R will swept out in this time dt will be simply the area of this triangle, that is OPQ, which I have actually shown in this figure by this shaded region. The area of this shaded region is actually swept out by the radius vector in time dt. Okay. So area vector swept out in this time dt. If it is dA, then this will be equal to area vector of triangle OPQ. Okay. Now let us try to find the area vector of this triangle OPQ. If you consider that the motion of this particle is taking place in xy plane, we consider that this plane in which the particle is moving under this central force is just a xy plane. You know, if this surface lies in xy plane, then its area vector will be in z direction. So this dA will be actually equal to dA k hat, where k hat is a unit vector. normal to this plane, that is along the z-axis. You know, area vector is always perpendicular to the plane surface. Okay. Now let us try to find this area vector. What will be this dA? You know, area vector dA, as I have told you, that if we consider that the particle is moving in xy plane, then this area dA swept out by the position vector in time dt will be in xy plane. So this area vector is in the direction of z-axis, and along the z-axis we consider the unit vector k hat. So dA vector is equal to dA k hat. And dA is actually area of that triangle, and that will be equal to what? 1 by 2 base into height. So what will be the base? Base is PQ, you can see, and height, that will be in fact OP or OQ. Both will be actually equal to R, because we consider that Q is very close to P. So OQ and OP almost are same, and this angle d theta is very small, this almost 0. Okay, so this will be in fact OP times PQ. Okay. Now let us put the value of OP and PQ. OP, you know, this is R, and what will be PQ? You know, theta equal to L upon R, arc divided by radius. So see this figure. So this this d theta, I am writing it here, d theta will be equal to what? This will be PQ divided by R, and so PQ will be R d theta. Okay, it is clear from this figure. So instead of PQ, we will write R d theta. Sorry, page has been turned, but this will be just okay. Don't worry, this is just a drawback of my device. This has been become old, and I will change this iPad very soon, and then this problem will be removed. So this you can see, this is R d theta. So sorry, I have not written the unit vector k hat. You have to write it. This is k hat. So this is 1 over 2 R square d theta k hat. Okay. Now let us find the time rate of change of this area vector. So what will be dA by dt? Because we have to prove in this property that the rate of change in area vector, or the which is actually called areal velocity. This dA by dt is called areal velocity. As you know, dr by dt is velocity, linear velocity. Just like that, at the place of position vector r, here is area vector, and so this is called actually areal velocity. Okay, so dA by dt, this will be what? This will be 1 by 2 r square d theta by dt times k hat. Okay. Now in dot symbol, you know, this d theta by dt is written as theta dot. So you can write this is 1 over 2 r square theta dot k hat. Okay. This is the areal velocity. dA by dt, this is called areal velocity. Okay. What is this dA by dt? dA by dt, you can write it VA, and this is called areal velocity. Areal velocity. Okay. Now see, this areal velocity we have obtained here. This is equal to 1 over 2 r square theta dot k hat. Now remember the results which I have discussed in the previous lecture. You have seen that the angular momentum of the particle is equal to what? Angular momentum of the particle moving in this plane. angular momentum of the particle moving in this plane. In this plane. You have just seen the result which I am going to mention here in the previous lecture, that J is equal to mr square theta dot times k hat. Okay. So what will be this r square theta dot k hat? This is equal to J over m, and I have denoted this J over m by the symbol h. This is angular momentum per unit mass. Okay, angular momentum per unit mass. Okay, so you can write in the light of this equation 2, equation 1 in this way. Instead of r square theta dot k, we will write either h, or we will write in fact J over m. J over m. So you can write equation 1 equal to what? Equation 1, this is actually dA by dt. This is written as J over 2m. J over 2m. Okay, or you can also write it h over 2. H over 2. But we have seen in the previous lecture that angular momentum J of the particle remains constant when it moves in a central force field. So J in RHS is a constant, and m is mass of the particle, and you know in classical physics mass is constant. So you can say that in fact the RHS of this equation 3 is constant. So as J or H is constant, angular momentum remains conserved in a central force field. So we can easily say that this dA by dt is equal to constant. And this is the property which I have mentioned, that the areal velocity of the particle moving in a central force field remains constant. Now in the alternative way, you have stated this property that the radius vector sweeps out equal areas in equal time interval. So now let us consider that this is the trajectory which is described by our particle in a central force field, and this O is the center of force. Now consider the particle is at this point P at time t, and this point Q at time t plus dt. T plus dt. Okay. So area described by this particle or this radius vector r in time dt will be the area of the figure OPQ. Now again consider that particle is here at this point, let us say r, at a time, let us say t equal to t prime. Okay, and at this point s, let us say it is at a time t equal to t prime plus dt. Okay, t prime plus dt. It means this area OPQ has been swept out by the radius vector in time dt, and this area ORS has been also swept out by the radius vector in time dt. Both time intervals I have taken same. Now as you have seen that this dA by dt is equal to constant. dA by dt is equal to constant. Okay. Now, if you consider that this area OPQ is equal to dA1, OPQ area is dA1. So dA1 by dt, that will be equal to dA2 by dt, where dA2 is what? This dA2 is the area of ORS. So you can say that this dA1 is equal to dA2. What does it mean? It means if you have considered that same time interval dt, then you can see that the area swept out by the radius vector drawn from the center of force to the position of particle swept out equal areas in equal time interval. Okay. So this property has been proved, and I hope the proof was very easy and you have definitely understand everything which I have told you. And this is just a very simple concept but very useful, and we will again study this property while studying the Kepler's laws of planetary motion. Now let us see the another property which I have mentioned, that central force is a conservative force. Central force is a conservative force. You know how conservative forces are defined, or conservative fields are defined? In fact, you know that if the tangential line integral of a vector field does not depend on the path, but it depends only on the initial and final position, then that field is actually known as conservative field. So let us see this figure. Actually, in this figure I am showing here that there is a particle at point P, and that particle moves to this point Q following two paths. Let us say first path is in fact this PAQ, and the another path is PBQ. Okay. And if this particle is moving under a central force field, then actually it is found that the F dot dr along the path PAQ is equal to integral of F dot dr along the path PBQ. It is seen in this case. And this shows actually that this tangential line integral, F dot dr ka integral means tangential line integral of F along the path PAQ. And this shows that F, which is actually a central force, this is actually of conservative nature. It is of conservative nature. Okay. This proves this. Okay. Now, you can see a very important result from this. You will actually see that the circulation of a central force is also zero. Circulation of a central force is zero. Circulation means if you find the tangential line integral of the central force along a closed curve, let us say this C is a closed curve, and if you find the integral of the central force F dot dr along this closed curve C, then you will see that it is equal to 0. And you know that if circulation of any vector field is 0, then that vector field is called irrotational, or that is also called a conservative vector field. So this result also shows that F is conservative. F is conservative. Okay. Again, as you can see that central force is a conservative force field, and you know any conservative vector field can be obtained from a potential function. Whenever the field is conservative, we always define a potential function with respect to that field. So, if V equal to potential, or you may also call it potential energy. In higher physics, potential energy is simply called potential. So if V is potential or potential energy, then we can derive this central force F as the negative gradient of this potential function, F equal to minus del V. F equal to minus del V. And in case of spherical symmetry, in case of spherical symmetry, we also say that this F is equal to what? This is equal to minus dV dr times r hat. Okay, times r hat. In fact, this del means gradient operator. This is for grad or gradient. So this result is also written as F equal to minus grad of V. Grad of V. Okay. So you can see from this result that if a potential function is given, we can easily find the corresponding conservative force or the central force which is responsible for that potential. Just in opposite manner, if you have given the central force and you want to find the potential function, the process will be just reverse. Here, for getting the value of central force, you differentiate the potential or potential energy, and so for getting the value of potential energy or potential, we simply integrate the this force. So if you want to find V, so this V of R, this is actually given as minus integral of F dot dr, or you can also write it equivalently as minus integral F of R and F of R dr plus some integration constant. Actually, the value of this integration constant is obtained on the basis by using the initial condition, or you can say the boundary condition. So this C is found by using the boundary conditions. And what will be those boundary conditions? The first condition which we use is V equal to 0 at R equal to 0, and the second condition which we use to find that integration constant is V tends to 0 at, as, not at, but as, you can say as R tends to infinity. Okay, R tends to infinity. So by using these conditions, we can find the integration constant, and after that you will get the value of this potential function or the potential energy function. So remember that this central force is a conservative force, and if it is conservative force, its tangential line integral will be path independent, its circulation will be zero, and we can derive this force by taking the negative gradient of the potential function corresponding to it, and by integrating this force with respect to r, you will get the potential energy. Okay, so these were actually the two important properties which we have discussed in this lecture. Now in the next lecture we will see a very important and last property of this central force field, and that is actually the conservation of energy. Actually, whenever a particle moves in a central force field, its total mechanical energy remains conserved. Since it is a conservative force, so definitely conservation of energy will hold, and that will be discussed in the next lecture. So definitely watch the next lecture too. Only then the all 5 properties of central force will be clear to you.